In this video, we're going to go over the Lab 3 worksheet, calculating some things on your exported data Excel sheets. So, and then also creating graphs and calculating a few things. So, let's take a look at your sheet. I have one of the sheets pulled up here on my right, and then I'm going to use the left as a reference for some of the calculations that we'll be performing. So, let's go ahead, and if you want to pull up one of your sheets and follow along, I'm going to go to the Lab 3. Here are the important equations that we'll do. We'll take basically our base measurements, what the metabolic cart will take, VE and BTPS, body temperature, pressure, saturated, the expired O2, fraction of expired O2, and fraction of expired CO2. So here I'm just going to call this calculations. Whoops. And here we'll start with VE. That's going to be in standard temperature, pressure, dry. I'm just going to give myself a little bit of leeway here and do justified left. There we go. VI, standard temperature, pressure, dry. We'll do VO2. I'll put the units in just a moment. VCO2, RER, and VE over VO2. And lastly, VE, well, actually not lastly, but VE over VCO2. Predicted VO2, measured VO2. Alright, so that will round everything out. We'll be performing these. Not all these are on that left side, as you can see, but a lot of them are. Just adding a few of these things for nice, oops, not text color, background color. Cool. Just to differentiate, saying, hey, this is what we're going to be doing. Okay, units. So liters per minute. It's going to be it for a few of these things. Keeping track of everything. Here, units cancel out, units cancel out, units cancel out. And here we're going to use different units. Milliliters per kg per minute. It's makes typing a little bit easier, and that's one of the reasons we're doing it. We don't have to type as much in those, which is nice. I like to save ourselves a few steps and tons of conversions if at all possible. Alright, so starting with VE, standard temperature, pressure, dry. We are going to take body temperature, pressure, saturated, and divide it by our conversion factor. Our conversion factor is on this sheet right here, standard temperature, pressure, dry to BTPS. That's calculated using the testing environment, temperature, pressure, and humidity. Okay, so the computer does that for us. We don't have to do it. I've checked it. It's pretty close, within 8 decimal places. So it's pretty good, I'd say. So we can do our calculations here. VE, standard temperature, pressure, dry. We're going to take this. Oh, if you're not familiar with doing functions in Excel, anytime we're going to do a function, perform a calculation, we're going to do equals to as our first step. So equals, we'll point to this cell and divide it by standard temperature, pressure, dry. Point to that cell. Now, and it's showing me what it's going to be. Now, before I hit enter, return, and accept this, I'm going to go to where this B20 is, points to standard temperature, pressure, dry. I'm going to add in a $sign. What that $sign does is it's going to say, hey, always point to this row of this column. Always point to B20. And then I can just come here and hit that to automatically apply it. Okay. Some of these things are in a different thing. There we go. Just looked a little funky. There we go. All right. So we have our VEs. The VE, standard temperature pressure dry, is always less than body temperature pressure saturated. So the volume liters per minute, the rate is always lower. So that's an easy indicator of, oh, all right, I got the right numbers. Now VI. VI is sort of the one that's a little funky here. It's a lot of steps. Taking one step at a time. So we'll use that VE, standard temperature pressure dry. We'll multiply that by, we're going to start with 1 parenthesis, 1 minus, start a new parenthesis. We'll do FeO2 plus FeCO2. Close one parenthesis, divide it by 100, and then close parenthesis. That takes care of the numerator here. So what we're doing is we're doing 1 minus FeO2 plus FeCO2. FeO2, FeCO2, those are fractions of the total air. We want to know how much of that total air is O2 and CO2 expired, and then we'll divide it by what was inspired. So divide it by 1, again minus, start a new parenthesis, and we need the inspired. Inspired's not on here. Where is it? Oh, it's right here. Right here are base sampling values. So O2 plus CO2 divided by 100. Okay, and close parenthesis. Okay. Now one thing before I keep going forward is I want this to always point to these base sampling values. So O2, CO2, O2, CO2. I need to always, again, dollar sign. Dollar sign says, hey, always point to this row of this column. And it should be very close to VE. Should be very close to VE. It can start out a little bit above while your oxygen system is getting up and being used, utilized for energy expenditure purposes. And then it will overtake it at some point. We can see it overtook it here, especially towards max. Cool, so that takes care of VI. Now we have VO2, so equals, here we're doing inspired minus expired. So how much was inspired and how much was expired? How much was extracted? How much did we extract? So the inspired divided by 100 multiplied by VI, subtract it from expired, parenthesis, FeO2 divided by 100 multiplied by VE. Okay. Now before I hit this and keep on going, I need to always point towards that base sampling. Always point towards that base sampling O2. There we go. We're always pointing towards base O2. Okay. Now here's a quick check. Are we on the right track? So here I can see that this person reached max at 7 minutes in. That's a little bit earlier than we would want. You can check on yours, see how far yours was. But this person reached max around here. What's nice is on our printouts, on our sheets, we have what their max was in liters per minute. And this is very, very close. 3.61360. Here it's 3.61359.8. There's a few rounding things that the computer does at 8 decimal places. Here we're using the full 15 digits, decimal places. So there can be some smallish rounding errors. At that amount of decimal places, it doesn't matter because that's less than a milliliter. That's less than a milliliter. It's of air, and that's very, very, very small. But again, we're doing it from base values, so we're doing pretty good. We don't have any rounding error yet. We don't have any rounding error that we're introducing because we're using the full values that we were given. All right. So if yours is not, go ahead and check back on VE, VI, or VO2 to make sure that things are pointing to the correct places and you have the correct $signs where they need to be. All right, so from here, VCO2 equals, we're going to do expired minus inspired. So expired divided by 100 multiplied by VE. Again, those are our expired minus inspired. Inspired again, this base O2 times VI. And before I hit return or enter, we're going to come up to base O2 $sign. All right, cool. So it should start out lower, and then it slowly increases, and it will get above when we are getting closer to VO2 max. Or for most people it should. For everyone in class it should, unless you're a very highly trained athlete or you quit early, one of the two. Okay, so here we have RER. This one's easy. VO2 divided by VCO2 divided by VO2. Okay, this looks like a real real RER number. We don't need any $signs in this one, thankfully. Makes it simple. Okay, now we have VE over VO2. So VE divided by VO2. No $signs needed. And VE over VCO2. All right, cool. Those weren't listed on here, but I know those are ones we have to perform. So just a quick check now. VE over VO2 and VE over VCO2 are used for our ventilatory thresholds. So let's come up to that. I can also show you on this document here. Here it wants you to create a graph based on that stuff. You know, when did they occur? Can also look at this table here. We can see it. We'll take a look at that. But ventilatory threshold 1. It's the point when VE over VO2 bottoms out and increases thereafter with an increase in work rate. And VT, ventilatory threshold 2, is VE over VCO2 bottoms out and then increases thereafter with an increase in work rate. Okay, so taking a look at this, we see this person reached at minute 2. They reached their ventilatory threshold 1. Okay, and then for VE over VCO2, reached it right at minute 3. Right at minute 3. So real quick, this tells me this probably was not a good protocol for this person to select right off the bat. For this person, it may be for your person or you or whoever data you got, but this is probably not a good protocol for this person because we didn't want them to reach it so quickly. Especially their VO2 max as well. We don't want them to reach their VO2 max within 7 minutes. Ideally. 8 minutes at the minimum. At the minimum, I would say. Ideally, shoot for about 10 to 12. No longer than 15, though. Okay. So that concludes those parts. Now, if we want to make some graphs. To make some graphs, we'll have to come over here to time. Holding control, it might be command on Mac. Then selecting here our VO2, VCO2, and whatnot. Now we'll come up to insert. We're going to insert a chart. This isn't what we want. Google Sheets isn't great for charting, but you know we'll make it work. We want to change this from a column chart to scatter for one, and this does some weird things. What we want on the x-axis is our time, which is A31 to 38, at least based on mine. Okay, and then I'm going to remove that from the Y series. Okay, so here we go. Bottoms out and then increases thereafter. Cool. You may have larger changes based on your data, but you know, this is what we got. VE over VO2. Now, if you wanted to say add those use row 27 as a header. Say you wanted to add axes, you need to add title VE over VO2 time for ventilatory threshold 1, something like that. You can change and add horizontal axis title and vertical axis title and whatnot, so make sure you add that stuff in. Okay, I'm just going to get that out of the way here. You also need to do that for VE over VCO2, so make sure you do that. Alright, so now we come to predicted VO2 stuff. This is going to be recalling from our previous week in Lab 2. Lab 2 we looked at predicting VO2 based off of walking speed, running speed, and cycling, and compared it to what was measured. We want to see, are we in the ballpark? With that protocol in Lab 2, we had you exercising for 6 minutes. We're taking the last 3 minutes of measurements. Here, there was a more constant change. It was changing after the second minute, it was changing by either 0.5 miles per hour or 1% or 2 of grade every other minute. So it was constantly changing a little bit. So you're never going to reach quite a steady state. But we want to see, are you close? What's going on? See if you're getting close or not. So I'm actually going to do the measured VO2. This one's a little bit easier. So what we'll do is we'll type equals to 0.2 VO2. We're going to convert it from liters per minute to milliliters per kg per minute. So multiply by 1,000 to get it to milliliters, divided by body mass. Okay. And one thing we need to do is we need to come up to the body mass and add that $sign. Okay. Drag that on down. If you try double clicking it, there's nothing in this column here right now, so it doesn't know. Excel is actually smart enough to know that, I know what you mean, but unfortunately Sheets isn't, so we got to work with it. Okay, so those are measured VO2 in milliliters per kg per minute, and again, this is a good check. Are we in the ballpark? 5.656, and then it slightly deviates from there, 7.3. So it's fine. We're within. This is milliliters per kg per minute. So this is like we're in microliters before we even get an air in this format. So we're good. We're doing fine. Now comes the predicted VO2 part. This one's a little bit trickier because, I'm going to show you how to enter these, based on your data. So here we have speed and elevation in column B and column C. You want to make sure, it doesn't need to be in column B or column C exactly, but if you have work rate, you need to make sure you point to the correct column. If you have work rate, make sure you point to the correct column, whether it's F or whatever. The work rate ones will have one less than this one. Here we had someone that did the jog. If you do the walk to jog, you'll have to do some parts the walk, some parts the run. So you need to make sure you do those. So to do those, I'm just going to show you the jog one. So equals, so parenthesis 0.2 times 26.8 times this. It's okay if I did it slightly out of order. Okay, plus 0.9 times speed times 26.8 times our grade. And that grade is going to be divided by 100. You need to get it from percent into decimal format. and then add 3.5. Okay, and I know because I've done this several times before, that about 5.5 miles per hour, 1% grade is about 34 milliliters per kg per minute. So I'm pretty familiar with that. So anyways, we have our data here. So this one I don't need to add any kilograms in or add any dollar signs in, sorry. So I can just drag straight down, easy peasy. So based on this data, this person reached max around here, and it's about 9 milliliters per kg lower. That could be true. It's a little bit low. This person might have reached max, although they might have quit just a little bit early based on the protocol too. If we had a more gentle protocol, we might have captured it a little bit better. Say if this person did the walk to jog versus the jog. We do not recommend people with a VO2 max of 38 to do the jog protocol because of this. They'll quit way too early before they have time to get up to the level of required VO2. So ideally, it should go a little bit slower, a little bit more eased into it. All right, so let's just say I had the cycling equation. So if I had the cycling equation, so equals to 1.8 times. I'm just gonna assume this is the work rate column. Now make sure you point to your work rate column, whatever it is in watts. So this times 6.12. Sorry, 2 parentheses. Divided by, that divided by, don't really need to, but I just do it for completeness sake. It's okay. Divided by body mass, and then plus 7. Okay, and then beforehand, gonna add in that dollar sign for the mass. Again, this isn't what the person did. We know it's not. Yep. Okay, so that's that. And then if I wanted to do the walking, so equals, actually, let's take a quick look at the walking. The walking on here, person does 4 minutes of walking and then does jogging. So the first 4 minutes will be equals 0.1 times speed times 26.8 plus, then we have 1.8 times speed times 26.8 times times elevation divided by 100, and finally plus 3.5. So it would be this. Again, this isn't the real number because this is not a walking speed. Walking equation only works between 3.7 at the highest and 1.9 at the bottom. So for the first 4 minutes, you could do this. However, past this, you have to do the running equation. You have to. Otherwise, it's not going to look right. You're going to get some weird data. So make sure your data is appropriate to the appropriate columns and whatnot. If you do have any questions, though, please shoot me an email or contact your lab instructor. I'll see what I can do. If you have that, make sure you also link me your documents so that I can just take a quick, easy look. We don't have to play email tag while we're waiting. Just let me know what you're having difficulty with and what you want me to take a look over. Send me the link to it as well.